Summary. Okay, so yeah, this is the summary for lesson 3. Okay, which you can see is a lot of video. Okay, 9 videos. Okay. Anyway, the first part we actually go through, right, if you remember, is to recap on last week amplitude decay graph. Okay, I don't talk about it anymore. And then we do tutorial 2. Question 1 is to familiarize what lesson 1 and 2 has taught us. So this part is actually belongs to lesson 1 and 2, but whatever. So now, after which then we derive the viscous friction damper, which is taking a lot of time, but it's also very beneficial for me to understand. And typically is an approach where we can always use this thing, understand the movement, draw FBD, you know. So we derive a lot of things. We derive the understandings, and then after that we do tutorial question 3, tutorial 3 question 2 to fully understand how does all this thing works. Okay, how does this thing being applied in questions and stuff like that. And it's a very good concept which the school, yeah, you have to really do a lot of things. So this portion will explain what are the key concepts here to actually take note. Okay, the very key thing is not stated here is that make sure 2 pi over the period, right? The pi, make sure you multiply inside is 2 times 3/142. Okay, please. It's a class mistake I always leave in. Okay, with that, and then next is I will just look out for what are the things as given parameters. When always given this type of graph, okay, when you're always given graphs, this one typically you have to understand the rotation and things. So you will be using this, okay. But as for those that are graphical, okay, that's where am I? For like graphical, okay, this is also I think is also also using this, I think. I haven't do yet lah. And then this one also doing that. So this is the graph only lah. I think, yeah. So typically when you do see a graph, the first thing you need to do is to identify the question first, know what the question is talking about, and then after which you know what the amplitudes, the cycles, the periods, the whatever lah, okay. So you have to know and understand it in a very detailed way. It requires skill. So apparently I have no skill also, so I have to practice. So you have to practice in the future. I mean, you are my future, so you have to practice. If not, I gonna fail again, and yeah, whatever. So shit, where am I? Oh yeah. So after that, you have to appreciate on the different cases approach for viscous friction. This is for the viscous friction equation. If you remember the viscous friction, we actually derive our general equation. Okay, this is the one we derive using our method over here. And then the key thing that I want you to take note is that for the case 1, case 2, and case 3, the only key concept here is that the general equation can be used to solve. Is adequate enough to solve for everything. Just that because when the damping factor itself comes in, okay, when the damping factor itself comes in, if it's equals to 0, larger than 0, or smaller than 0, equals to 1, over 1, larger than 1, or smaller than 1, different scenario come in. Only larger than 1 will this equation be used straight away, okay. If it's equals to 1, which is critically damped, then you have to use this equation and the equation that I've actually derived in here. In here. So this is the phase shift, while the R itself is the square root A square. I mean P square plus Q square. Okay. While this phase shift itself is from my book itself is it's some tangent thing, okay. Okay. Anyway, I also don't know what the fuck is that, but Yeah, you can go and search it out lah. Yeah, it's in my math videos. Or maybe I go and search it out for you. Hold on. So the alpha itself is equals to tangent P over Q. Okay? And then yeah, where are we? So if it's under them or so called a subcritical then it's this one okay? If it's otherwise then you have to go if it's equals to one when it's equals to 1, the whole equation will eventually goes to 0, which is very hard, which we cannot find anything, we don't know what the hell is it. So apparently we will because eventually you get this, you cannot do any general equation for that. Okay, you have no answer at all. So this is why we introduce this equation, this case 2 equation. The method of deriving this I have no idea. Okay, but you just use this here. Okay, remember. It's not in your formula sheet. But however, as he say, as the lecturer say, this one is the most important one. That a way that perhaps you may need to know. I don't know. So yeah. Anyway, and then concept of critical damping coefficient. Okay, what the hell is that? Okay, if you just remember, this is just a video ago. Where am I? This one. The C and the C naught. C naught is the critical damping where there is natural frequency. Okay. Where there is no damping. Yeah, correct. Where there is no damping, the thing oscillates. Continuous mode oscillates, which is like that. Okay. So you can also say that this is C. Okay, the coefficient for damper, and this is C naught, the coefficient for. Okay, sorry, no. Yeah. No. Sorry. Yeah. This is C lah. Okay, I have no doubt. But for C naught wise is when your damping factor is equals to 1. Okay, it's a comparison. When it's equals to 1, then this is C naught, the critically damped. Just nice that it damps up all the oxidation. Okay, so yeah, this is the concept between the critical damping coefficient, and then the W and Wn awareness in the formula sheet. Oh yeah. Okay, so what is it is that when you see this equation, don't think that this is Wn, this is Wn, or this is Wd. Both there are there are two frequencies in this equation. One is the natural frequency, one is the damping frequency. And then the differences of them are that, as I say earlier, as I showed you earlier, is the graph itself. The damping frequency has a damping effect that will eventually decay to 0, okay, when time is equals to infinity. But for natural frequency wise, you will keep going and ongoing like forever, okay, like seriously, like no life lah. Yeah. And then concept of critical damping coefficient, I think I just said. So yeah, why am I repeating? Okay. And then find undamped frequency, then okay. So as for then question temperature what temperature where is it? Where am I? Where am I? As for the tutorial 3 question 2, the one that we just finished, what are we saying? Oh, we have to first find our undamped frequency first, okay, which is our WD. I mean W find damped frequency. Find damped frequency. Sorry, 5 damped frequency. Okay, and then you find your damping factor, and then you get the rest. The reason why is because from this equation, as you can see, this equation, the WD is equal to the natural omega 1 minus damping factor square. So therefore, if you find this and you find this, because typically the graph itself is given in this direction, I mean in this motion, so you will know that this is in fact natural frequency. I mean, in fact, damping frequency. Damping frequency wise, you know how to find 2 pi over t. The period itself is 1 period. Okay, from here to here. Okay, and then where are we? Oh yeah, and then Oh yeah, cosine, sine, wherever variables that that deals with cosine and sine. Let's say sine some angle. Make sure the angle you are talking about is radian. Okay, when you key inside calculator, it's radian. Okay, so yeah, and then that's all. I'll see you then next sometime. Bye bye.